We can discuss the partial wave analysis, the second part of it. So in the last class, what we have shown is it is possible to expand any wave function in terms of spherical harmonics in this way, but this R and L is the radial part of the Schrodinger equation, and it is possible if the potential is spherically symmetric. Okay, so we are going to utilize this information in our today's lecture. Okay, so basically we are going to analyze scattering problem using this partial wave technique. Okay, so the actual scattering problem is we'll have some incident ray, the incident radiation. The incident radiation we can treat as the plane waves, which is can be written as e raised to I k0 dot r, and there will be some scattering center, and from the scattering center the particle will be scattered towards some direction, the scattered wave. Okay, so the original unscattered direction is along this, so better we can have a coordinate system here. So let's suppose this is your original incident direction, and it's mutually perpendicular direction, and the direction perpendicular to the plane. Okay, so let us this be z, then it can be x or y. Okay, so the angle of scattering, so this angle we can denote by symbol theta, and the angle phi. So angle phi we can found by projecting this. Okay, so we have to project this vector on the xy plane. Let's suppose this is the projection on this xy plane, and this angle would be phi. Okay, so our incident direction is k0. So therefore k0 dot r, I can write the magnitude of k0 r cos theta. And your incident wave we can write e raised to I k0 dot r. So this is the incident wave function psi inc. So this we can write e0 e raised to I k0 r cos theta. Now it is possible to expand this incident wave in terms of the spherical harmonics as sum over L comma m ALM RL of KR. So basically it would be K0R, then phi LM theta phi. Okay, so what is this YLM? So YLM is the spherical harmonics. So I can express this YLM in terms of the associated Legendre polynomials. So YLM theta phi can be written as 1 upon root 2 pi, the coefficient CLM, PLM cos theta, e raised to I m phi. Okay, so let us keep this as equation number 1. Now if you look at equation number 1, the right side contains r theta phi, but left side contains only r and theta. So therefore the right side, in the right side the term phi should vanish. Okay, so how the phi dependence would vanish from the right side? So phi dependence on the right side would vanish if there is no e raised to I m phi term in equation number 2, and that is possible if you set m equal to 0. Okay, so that is the argument. So if you look at equation number 1, So in equation number 1, the RHS of equation number 1. Okay, so we can start with LHS. So LHS of equation number 1 is independent of phi. So therefore RHS should also be independent on phi. It is possible if we set m equal to 0. So if we set m equal to 0, so this become yl0 theta phi. So we can make this equation number 2 will have yl0 that would be equal to some constants. Okay, then pl m cos theta become pl0 cos theta, that will be simply the legendary polynomial pl of cos theta, then e raised to 0, that would be 1. So that means if m equal to 0, then the spherical harmonics will be simply become the legendary polynomial. So therefore I can expand my psi incident, the incident wave function can be simply sum over L, some expansion coefficient may be written as AL, then R L of K0R PL of cos theta. So the next task is what is the form of RL of K0R. So remember this RL of K0R should satisfy the Schrodinger equation. Okay, so the equation satisfied by RL of K0R is minus 1 by R square d square by dr square R RL of K0R plus L into L plus 1 upon R square RL of K0R plus V of R RL of K0R equal to 2 mu E upon H bar square RL of K0R. Okay, so the solution, so this is called the radial part of the Schrodinger equation. So this radial part of Schrodinger equation, such Schrodinger equation has a solution in two forms. There are two possibilities. So this RL of K0R can be written in two forms. So one is it is proportional to R raised to L, and one is it is proportional to 1 upon R raised to L plus 1. There are two possibilities. So this first possibility, C times R raised to L, called the Bessel function or spherical Bessel function. And this part, the second part, is called the spherical Neumann function. Now this equation must be valid at all possible R, but the problem is this term, one of the term diverges when R tends to 0. So which term diverges when R tends to 0? When R becomes 0, when R is very small, the spherical Neumann function diverges. So therefore it is not a possible solution. Okay, so this is not a possible solution because it diverges when r tends to 0. So hence this K0R takes spherical Bessel function, and the spherical Bessel function we denote as JL of K0R. So hence the incident wave function psi in of R, we can write sum over L AL JL of K0R PL cos theta. Okay, so we have expanded the incident wave function in terms of the spherical Bessel and the Legendre polynomial. So our next task is what is the AL, this expansion coefficient. So this expansion coefficient we can find by using the orthogonality condition of Legendre polynomials. The orthogonality condition of Legendre polynomial is given as integral -1 to +1 P L of cos theta P L prime of cos theta d cos theta equal to upon 12 plus 1 delta LL prime. Okay, so then let this be equation number 3 and equation number 4. So what I will do is I will multiply PL prime cos theta in equation number 4 and integrate the entire expression with respect to d cos theta from -1 to +1. Okay, so what I will do is I will take the equation number 4. Equation number 4 is sum over L AL JL of K0R PL of cos theta, and I will multiply with PL prime of cos theta and integrate over d cos theta from -1 to +1. So remember, this term is nothing but e raised to I K0R cos theta. So therefore this integration can also be written as -1 to +1 e raised to I K0R cos theta PL prime cos theta d of cos theta. Okay, so this sum over L can be taken outside, AL can also be taken outside, and if you integrate it, so AL JL of K0R can also be taken outside because integration is over the cos theta. So then if you take all the constants with respect to theta is taken outside, then we'll get an integration, and that integration has this orthogonality condition. So PL cos theta, PL prime cos theta, d cos theta, and its result is simple. It is 2 upon 2L plus 1 Dirac delta, sorry, Kronecker delta L prime, which is equal to this integration. Now, how to perform this integration? So we can take this as first function, then second function. We can use the product rule. So the product rule is first we'll keep the first function PL prime cos theta, then integrate the second function e raised to ik0r cos theta divided by ik0r and put the limit, and the limit would be from -1 to +1 minus the integral of the derivative of the first function, which is d PL prime cos theta divided by d of cos theta then the integral of second, so integral there is to I k0 r cos theta. If you integrate again, so if you integrate this, what you will get is e raised to I k0 r cos theta divided by I k0 r, then d of cos theta. Okay, now the thing is, if you look at the RHS, that contains e raised to I k0 r cos theta upon I k0 r. So if you integrate once again, you will get 1 by r square term. So the second term would be very small compared to the first term. Okay, so therefore it is possible that we can neglect this the second term compared to the first term, because the first term has 1 upon r dependence, whereas the second term contains 1 upon r square dependence. So when r becomes large, the second term will vanish very quickly compared to the first term, or the second term would be negligible compared to the first term. So we can neglect the second term over here. Okay, so we can take only the first term. So therefore this become p l prime of 1 e raised to I k0 r minus p l prime of minus 1 e raised to minus I k0 r all divided by I k0 r. And what is the left side? So we have to sum over L. Then there is a canonical delta LL prime. So we have to replace all L with L prime. So it become a L prime J L prime of k0 r 2 upon 2L prime plus 1. Now recall, our aim is to find what is this AL. So we can replace the under L prime with L. So hence what we will get is AL times JL of K0 R 2 by 2L plus 1. Okay. Then on the right side we'll have 1 upon I K0 R can be taken commonly. Then PL prime of 1 is simply 1, whereas PL prime of minus 1, it will be minus 1 raised to L. So this is simply 1, and whereas it is minus 1 raised to L prime. Okay, and we have to replace L prime with L, and it becomes e raised to I k0 r minus raised to L e raised to minus I k0 r. Okay, so let it be 1 by I k0 r e raised to I k0 r minus 1, I can write e raised to I pi raised to L e raised to minus I k0 r. Now we can take e raised to I L pi by 2 commonly outside from right side. So e raised to I L pi by 2 divided by I k0 r. So this become e raised to I k0 r minus L pi by 2 minus e raised to minus I k0 r minus L pi by 2. So this become e raised to I times L pi by 2 divided by ik0r. So this we can write as 2I times of sine of k0r minus L pi by 2. Okay, so this is about the right side. Now we can simplify the left side as well. So the left side is the spherical Bessel function. Now we are going to use a result for a spherical Bessel function which is JL of K0R. So this can be written as for r tends to infinity as 1 upon K0R sine of K0R minus L pi by 2. Okay, so we can use this result for spherical Bessel function. So then the left side become AL 1 upon K0R, the sine of K0R minus L pi by 2, 2 upon 2L plus 1. So some common terms can be cancelled. So this K0R can be cancelled, sine can be cancelled, I cancelled, 2 can also be cancelled. So hence what would be your AL? So this shows that AL is simply e raised to I L pi by 2 to L plus 1. So now we have got the expansion of AL, the expression for AL, the expansion coefficient, which is e raised to I L pi by 2 to L plus 1. Now this can be equation number 5. So now we can substitute this equation number 5 in equation number 4. So hence the incident wave function, which is psi in of r, which is also written as e raised to I k0 r cos theta, can be written as sum over L e raised to I L pi by 2 to L plus 1 JL of k0 r P L of cos theta. Now what is e raised to I L pi by 2? So e raised to I pi by 2 is cos pi by 2 plus I sin pi by 2. So it is simply I. So hence the incident wave function psi in of r, which is e raised to I k0 r cos theta, can also be written as sum over L. The first term can be simply I raised to L to L plus 1 JL of k0 r cos theta. Okay, so we have expanded the incident wave function in terms of the spherical harmonics and the legendary polynomial PL of cos theta. Okay, so for the time being, we can stop our discussion here. And what we'll do is we will expand the entire wave function in using the partial wave also. And from that, it is possible to find uh, the scattering amplitude and the differential scattering cross section. So that is the key idea. So first we have completed the first part of our problem. We have expanded the incident wave function. Actually, we have started expanding the incident wave function in terms of the spherical wave, but in turn, as due to the spherical symmetry and all, what happened is that incident wave function now simply become the expansion of the spherical Bessel function and the Legendre polynomial. Okay, so there is no need to use this YLM. The spherical harmonics is not required for the time being. Okay, so we'll see in the next class with more details. So till the time you can study this particular derivation. Okay, so we required the same logic in the next session. So be prepared with in next class. Thank you.